Hello, everybody. It's my pleasure to talk to you today about the subject, velocity and depth conversion. And actually, before starting that, let me give you some resume about myself. My name is Ali Bakr. I have almost 42 years of experience on the oil industry, especially on the exploration and development. And actually, I spent this with majors and minor companies. So the majors include Shell, Phillips, Apache. However, Apache sometimes some guys consider it as the minors. Phoenix, IBR, and other many joint venture all over the 42 years. And I have my PhD from Cairo Leicester University in 1995. My background is geology, BSc in geology from Alexandria University, 1980. And actually, I have a diploma on geophysics on 1984 from Alexandria University as well. And actually, I'm well furnished with strong background on the acquisition, processing, and interpretation during my career. And I've ended my job with being an exploration manager for IBR, and then I joined Shell for 7 years as a workflow consultant, doing all the workflow for all the interpretation from A to Z for the Middle East, MENA, North Africa area. And now, actually, I'm teaching at the American University in Cairo, in Alexandria University in North Egypt, and in Cairo and in Ain Shams universities in Cairo. So I'm quite busy with the teaching. At the same time, I'm a consultant and have a small entity called RockServe. Also, we are doing a lot of work, starting from exploration and ending by field development plans and setting a dynamic models. Anyway, this is just a paragraph about myself. Let's go ahead and start what we're talking about, which is the velocity and depth conversion. And actually, something very important to tell you that I'm not going to go with equations and equations and equations. I'm going to directly hit the principles. So I don't know actually the background of the audience. So I just mixed the slides to include both the starter or the fresh graduate or even 2 years or 3 years of experience up to 10 years or 15 years of experience on the seismic interpretation. So it's a little bit interesting mix. And for the guys who got experience, I want them to be a little bit patient because we are going to go through some of the important basic details that you have to keep in mind while you are doing any kind of velocity studying or velocity using for the depth conversion. And also the audience who are a little bit starting their green projects or 2 years or 3 years of experience, I would like them also to be patient because a lot of the stuff going to be served the other experienced guys. So let's take whatever we can get, a flower from each garden, and come up with something that you could use it directly on the topics itself. For the velocity, actually, this is what we call it. This is one of the most complicated issue for all the interpreter. None of the interpreter have been using the velocity, and he's comfortable about what he's doing. Usually, we have a lot of uncertainties accompanied with the velocities because the resources of the velocity itself. But I'll start with you with the simple basic that we have to keep in mind while we are using the velocity, from where we can choose the best velocity that we're going to use it for our depth conversion after that. In the front of you, actually, I'm just put one of the AAPG and SAG cartoons about the velocity as a key. And actually here I'm putting VP and VS as directly related to the velocity of the shear waves and velocity of the B waves, both of them together. While in most of our work, we are not using the VS, only for the DHIs and AVO, we are using the VS. But in most of the work, we're using the VP most probably. But different things you are using the velocity on the seismic processing, on depth conversion, on rock fluid production, on well placement and drilling, forecast of the well tops, and also the sources of this velocity could be logs, could be VSBs, could be check shots. And then we go to the well appraisal to drill. So from all of this, you can see that the velocity is the key or one of the key in order to open many doors into many things. At the same time, those doors are open to come up with suggestion for the velocity itself. Let us start with the first slides on my the slides is talking about what I just have mentioned on the previous slide, talking about you need velocity for basin modeling, you need velocity for the prospecting, changing from time to depth. You need the velocity in order to calculate volumetrics and the economics, and also you need the velocity to develop the well. Everything on every step of our work needs velocity because we are working all the time domain. All the reality of the wells, the reality of the depths is on the space domain. So we need to change from the time to depths. Now, very important things that there is some assumptions that we assumed in order to get the equations of the velocity itself. Those four assumptions, many of us are not aware with them, and they treated the seismic like a magic. It's not a magic actually. It's have limitation either vertically and horizontally, and we need to take in consideration the acquisition and processing at the same time on those assumptions in order to treat what we have as an end product of the seismic section, and we understand exactly what kind of assumptions we are talking about. So actually we are talking about four assumptions at the theory of the dispersion of the B wave and S waves. Those assumptions are that the surface of the earth is a flat, which absolutely not. Also, we have mountains and we have valleys, so we have irregularities. Then we are using the bedding plane between the beds also are horizontal, which is never happened. It's usually dipping. If we're talking about 2 degrees of dipping, it's a dipping. So it's not horizontal. The third thing is that each single layer is a homogeneous, have one interval velocity. Again, it's not the case all over the business. The fourth one, that the ray path transmitted and reflected vertically, which practically it will never happen. We never put the source and receiver over each other at the same point and then receive whatever coming from the subsurface. So those four assumptions, very simple, very basic, that someone need to take in consideration. I don't know if I see some question directly here. No, not yet. Okay, because I can see that the Q&A there is 2. Okay, no questions. I saw there is some question, but no. Anyway, let us consider those 4 assumptions and see what will happen. Now, the surface is flat, as you can see on this slide. The surface is flat. The interbeds between 2 beds also flat. The second. The third, this is homogeneous layer, and this is another homogeneous layer. They have 2 different interval velocities, but it's homogeneous all over the layer. This is the third assumption. The fourth assumption, that the source of the waves like a ball, and it goes directly, as you can see, and then reflect at the interface. When it's reflect and the interface, it's come up with our what we call it reflection. This is what we assume. Well, this is not happening on the real life. We're not doing this. We're not putting the source and receiver at the same position, but we are putting the source and receiver aside from each other. So the 4 assumption got to be done with 4 correction. You have to make 4 correction for the 4 assumption. The first assumption, which is the earth is flat, we're doing what we call it static correction on the processing. And then for the interface, which is assumed to be horizontal between the 2 beds, we have the solution for this during the migration on the processing. Yes. Then this is exactly what happened, that the source and receiver are not on the same position. However, there are distance between them. So there is a source, and then reflection point, and then receiver. So we have to calculate for this correction to be on the same level, and calculate for the source, what we call it source static and receiver static. Both of them, assuming that the reflection, as you can see it in this way, that it's a ray reflection. Yes. Again, this is not the case in reality. Then actually, with different sources and with different receivers, we have shot S1, receiver S1, shot S2, receiver S2, shot S3, receiver S3, and then this has become now not only depth point, but a common depth point, because many reflections, more than one, have been come to the same point and reflected from the same point. Now, in order to do whatever we want to do to make it like vertical reflection, we have to do what we call it on the processing center normal move out correction, where we can sum those three reflections to come from one reflection, as you can see now on these cartoons. So the X1, X2, X3 are the three distance between source and receiver. And then we do what we call it velocity analysis. Now you heard the first name of velocity on the processing itself, which is velocity analysis. We do this velocity analysis in order to come up with the reflector to be flat. And then actually it's not the reflector flat, but the reflection from the different point. So we can stack them together. And for us, it is almost the vertical reflection. Actually, and it's not typically vertical, but we consider the first shot to receiver at a small distance with some correction to be vertical. And then after that, we can continue with the other corrections. Okay, now this is exactly what happened. X1, X2, X3, we have a reflector, and then the second reflector, and this is represent a reflection point, and this represent a reflection point, but still assuming that the two reflectors are horizontal. How we do that? In the processing, we do it through what we call it a velocity analysis. Now, if the reflector is dipping, as you can see it in here, then again, this is need another correction, which what we call it dip move out. So the vertical one, which is the normal move out, and then assuming the horizontal is the beds are horizontal, and now it is dipping. So we have to again do what we call it stacking velocity with increasing the depths. Now let us see this, and then we come up with some very good definition that will help you on driving and understanding all the velocity issues. Now, if it is dipping, as you can see here, so it's assumed that it is here, but actually it should be coming perpendicular to the surface itself. It should be coming that way. So that now we have to do a correction, moving this thread into this new position, and this is what we call it migration. We do this during the processing. I think most of you are familiar with this type of correction. I just wanted to tie how this correction are important and what is how we can calculate this correction or do a correction for them using what we call it velocity. So we mentioned velocity for the stacking, we mentioned velocity for the NMO, no normal move out, and we mentioned velocity for the deep move out, and then we mentioned velocity for the migration. All of these velocities that we are using right now, we don't have any source from wells that measure it, from check shot as example, or VSB. It's coming by what? By estimation. So it's a kind of estimated velocity. When I say estimation, it does include uncertainties, because it depends on estimation. So I have to estimate 3 or 4 values and select one of them. So once we said it is estimated velocity, then we know that there are a lot of uncertainties. This cartoon in the front of you telling you how we are migrating the dashed line into its real dipping in the processing using the velocity of the migration velocity. Now, this is an example for how the migration do for you using the velocity. So actually, on your right-hand side, you have a very nice syncline and another syncline, while actually the left-hand side is the diffraction coming without migration. So if you didn't migrate this with the right velocity, you will never be able to see the one on the right-hand side. So migration is very important. It's increase the resolution and bring the real structure in the front of you, and that's why we need to do the migration. Now, I would like you to see something interesting in here. Another thing for the migration, So to the left-hand side, it's not migrated. For the right-hand side, it's migrated. As you can see that the size of the anticline changed on that domain from that size to that size. So the anticline becomes narrower, more steep. The left-hand side is before migration. The right-hand side is after migration. All of this done by migration velocity. Now you are aware with what we call it estimated velocity. But actually, we don't have only the estimated velocity. We have three types of velocities. We have measured velocity. Take care about those simple definitions because we're going to use them directly to collapse the mountain of complexities for the velocities. Those simple definitions will make you understand exactly all the velocity types and go from one to another without any problem, assuming that you know all the basics of the equations itself. So that's why I said we're not going to talk about any equations in here, but we're going to fix some important simple principles that we're going to use it in order to simplify the world of velocity. So actually, I divided myself during my experience the velocity into measured velocity, and I put it at the top because it is the most important, and you get the measured velocity, you measure them in reality. As example, on the vertical seismic profile in the well, or from the check shot, or from the sonic. So you put your G phones inside the well, and at the same time you have the source of the waves outside the well, very near to the well, either very near to the well, very small distance, or more or less than that. So it's become what we say it that the source itself is more or less rig source, very near to the rig. Okay. So this is the measure type of velocity. Now it's VSB, check shot, and sonic. Think about it. What is the difference between the three types? What's the difference between the velocity that we measured from VSB, from check shot, or from the sonic? What's the main difference between them? Actually, the sonic is what we call it instantaneous type of recording of the velocity reading. So it's at the resolution, the sonic is the best because actually it's record all the velocities for each interval, each single feet of the well. So it looks very detailing, showing the velocity inside the well. The sampling is very dense sampling during the sonic, and that we call it an instantaneous type of velocity. Now, but as it's good, it has some disadvantages. The sonic, it's very good, but usually the first part of the sonic, it's never recorded in the oil business because it used the first tubing, which we are not interested on the first part, the first shallow part of the wells. So we never recorded the first part. The second things about sonic, that the sonic have very erroneous reading against shale, where the sonic read more or less the mud cake and they read more or less the holes rather than reading the real formation. So it have those two problems. So now we know it's very good, it's very dense, it's instantaneous at any depth you can get a reading, but it got those two disadvantages in our world. Now going to the left to the check shot. The check shot doesn't have the problem of the sonic. It covers from the surface of the earth until the TD of the wells. So that's good. But actually the sampling of the check shot is not as instantaneous as the sonic. The sampling in this case usually 100 feet or more interval. So it's sparsely more or less distributed all over the well. So it does measure the velocity, but each 100 feet max. Now moving from the check shot to the VSB to the left, then the VSB is more dense levels than the check shot. We shot as example every 20 feet or every 15 feet or every 25 feet. So it's the sampling is better than the check shot. However, it doesn't reach the sonic sampling itself. At the same time, it's measured from the top of the surface to the bottom, and the both check shot and the VSB can run on any open hole or in a cased hole, no problem. The good thing about VSB that you can run it either from zero offset from the well or from offset of the well, or even for deviated wells, you can still run it. And a lot of many types of VSBs are available on the market until what we call it 3D VSB, where you can shoot from different direction around the well. But all of them are measuring what? Are measuring interval velocity for the formation inside the well. That's good. Yeah. Actually, the sonic, the check shot and the sonic are measuring the vertical velocity perpendicular to the bedding plane. The sonic is measuring the check shot and VSB are measuring the horizontal velocity, while the sonic is measuring the vertical velocity. There is some difference between the vertical velocity and horizontal velocity. It's not a big issue, but at the same time, the end of the story that the measured velocity measured the interval velocity. If you do have Dex equation, you can change from using Dex from interval velocity into an average velocity and come up with the average. Take in consideration that in reality, sonic, it does not measure velocity. It does not measure transit time. It measures slowness. Take this in consideration. It measures what we call it slowness. So the slowness is the reciprocal of the velocity itself, and then from the slowness we can get the transit time. From the slowness we can get the interval velocity. Now, take in consideration that measured velocity at the top because it is the best type of velocity that you can use it in order to do any kind of depth conversion. Now, in our mind, we ranked them at the first. Then the second is what we call it calculated velocity. You have the simple equation of the velocity with the time, with the depth, have a very nice relation. So the distance equivalent to the time times the velocity, you can get the distance. The distance in our case is the depth, and the time is one-way time to the target, and then what we call it calculated velocity. Use calculation. And actually, I can guarantee that 80% of the explorationists are using what we call it pseudo average velocity, where the interpreter will pick his horizon at the well location and get the 2 time from that horizon, and he do have the well depth, and he use the time depth pairs measuring the time to the target, and he had the depth to get a kind of velocity. This kind of velocity, it's not an average velocity. We should mention it with pseudo average velocity because it's not measured. If it's measured inside the well, then we can call it average velocity, but we call it pseudo average velocity because it depends on the interpreter. If the interpreter was wrong and he didn't pick the maximum peak or the maximum trough or the zero peak or the zero trough, he's gonna use them for the equation, and then he come up with a velocity that it's not even find in the world. It's something belonging to his picking. That's why we have to make sure that we are differentiating what we call it the pseudo average velocity and average velocity. Some of the books are saying it's an apparent velocity, but actually the right name it's a pseudo. It's not an apparent. It's a pseudo average velocity because actually it depends on the interpreter himself. Those kind of velocities we come up on the category number 2. Now, the category number 3 that we started with at our lecture, which is estimated velocity, that we estimate the stacking velocity, we estimate the migration velocity, we estimate the dip move out in the processing. So it's a kind of estimation. Now, you rank in your mind that if you have a sources of velocity, you have to rank them this way. Which of them are measured? Which of them are calculated? Which of them are estimated? Now, if you do have the 3, then you can make up a mix of the 3 in order to have a nice, very nice velocity model. Because actually, both of the VSB, the check shot, and the sonic are restricted to the wells. However, in between the wells, you don't have sonic, you don't have check shot, you don't have VSB, but you do have shots point, and each shot point of the seismic or each trace of the seismic got a stacking velocity and migration velocity. So the good thing about the estimated velocity in this case, that it is distributed all over my survey. all over my 3D. If I have a 3D, I have each 50 meter or each 25 meter, I have a measuring for the velocity, for the stacking velocity. If I would be able to calibrate this velocity, which is an estimated, got a lot of errors, with the wells, then I come up with something that's calibrated all over the area. So it depends on how far and how can I do this calibration in order to have a nice model for the velocity. Now, this is exactly one of the most important slides in my teaching that I all the time give an attention to follow it very simply. Yes? Now, in order to go to the different velocities, I just put it in the front of room. So velocities could be processing velocity and vertical velocities. The velocity one, the processing, which is migration, stacking, NMO, and root mean square. And actually, root mean square, it doesn't have any property for the rock. This velocity have no meaning for the rock. If it's high, if it's low, it doesn't have any meaning. But the other ones does. So this one does not reflect a property of the rock. Now, to the left, vertical velocities, the interval, the average, the instantaneous that comes from the solid. And actually, we call it sometimes vertical, while we know it's not like what we have on the surface seismic ones. I put in the front of you actually how those velocities react with time, which is not our case in this case. Take in consideration that the velocity by the depths have an assumption, the fifth assumption, that the velocity is increasing with depths. We assume this. Practically, reality, no. You can see that sometimes the velocity decreasing with depths. If you ask yourself, how can it decrease with depths? Because the compaction increased by depths. Simply, sometimes you have some of the zone that's porous and got some gases on it, and it drop its porosity drop its density dramatically, and its porosity increasing, and you do have very nice interval where the velocity decreasing. And so it causes a lot of high amplitude. And this is one of the ways that we use it on the AVO in order to detect the hydrocarbons. The velocity have many parameters to work with. So in porosity, as you can see it, velocity increasing by depths, and as you can see it, while it is decreasing by increasing porosity, while it's vice versa to density, it's a little bit react differently with temperature. It's a little bit like the density and the grain size, both of them have the same trend. And actually the very interesting gas saturation, because the velocity could be the same velocity if you have small amount of gas on the sandstone or saturated with gas. They could give you the same velocity. Then frequency doesn't have so different. The overburden pressure and pore pressure, both of them have variation curve different than the other. We need to understand the behavior of the velocity with each one of these parameters. Just to realize exactly, I'm advising the guys who are working on the quantitative interpretation to look over each one of this variation in an intense way, to understand the porosity velocity, the density velocity, the temperature, the grain size, the pore pressure, the overburden pressure. All of them are very important for those guys. And also the other one are very important for the drilling guys, which is the overburden pressure and pore pressure. Very important for them. And this is actually conclude what I said before. Increasing velocity, increasing as porosity decreases. Yes. So compaction increase in this case. Observe it to increase in density increase. Little bit some change. And also there is change 5%, which until to 100 degrees. All of this actually you can come back to and refer to the lecture in order to come up with a conclusion about. Actually, I put them on 10 changes with the velocity. When the velocity change, this parameter change. Now I'm going to jump directly into the sources of velocities. The sources of velocity could be sonic, as I mentioned, or borehole check shot, or VSB. All of them, as I mentioned, This is just for you if you want to be aware with what kind of data acquisition we acquire in this case. And as I mentioned, in the case of the sonic logging, we are more or less looking for a very narrow area around the well itself. So it doesn't go faster or doesn't go laterally, while in case of the seismic, it goes more laterally. So this is the main difference between them. But by mean of the other, there's some corrections that we can do it for the sonic velocity in order to more or less come up with figures very near to what we use in the case of the check shot or horizontal. And in the case of VSB, actually, we are not only measuring the velocity for the VSB because of to get the velocity, but we need many things from the VSB. It's not our time now in order to talk about the benefit, because actually the slides here are part of a very big part of velocity. So I'm not going to go into the details why you are using the VSB. There is many things rather than getting the velocity to get it from the VSB, like prediction ahead of the beds, like looking for minor faults beside the well, like fracture orientation. All of this are coming from the VSB. I'm not going to go more than this, but this is just a cartoon for the how we measure at the VSB. If the distance D is a small, we call it rig source. And this distance is nothing. It's 40 meter, 50 meters small. And actually, we get the reflection of the downgoing, in this case, to the recorder, or even a reflection upgoing. And then during the upgoing and ingoing, we are separating them at the processing to get our representative for the waves itself. They measure the velocity and related to the time. For the VSB, also I'm going to jump this. I'm going to show you that the different type of VSBs in the front view are the rig source, zero offset, walk away, deviated well, 3D VSB, different type, all of them. But by the end of the day, this is one of our measure the velocity that we use it. Then the processing of the VSB, we should be aware with it. I'm going to jump this as well. It's not our target here, but I'm just telling you that this is the steps that the check shot we go through in order to measure and separate data. By the end of the day, actually, we have our VSB in the front of us. And in the front of you, actually, here, to the right, you have the VSB data, and to the left, you have the VSB data before the processing and after the processing. To the right, after the process, and you can see that the reflectors can very tie with the seismic to the right-hand side. Very nice tying between them. And this is actually what we are using the measured velocity in order to do. The good things about the VSB that it has two scale, one scale for time and one scale for depth, because you use the velocity, and in this case, you can directly use this data in order to tie the well into your seismic. And this is what we call it corridor stack in here, where we get the front of the VSB and we stack them, and we got the corridor stack, and we correlate this corridor stack with our seismic data. Again, I'm going to jump on the acquisition and processing of the and come up with an end result for the zero offset VSB. As you can see, very nice stuff in the front of you, and the corridor stacks in the front of you, and then the synthetic seismogram calculated after that, and you can correlate each event of those with your VSB data, and you can correlate even with your seismic data, and come up with time depth pairs. Those time depth pairs, so say you have 5 reflections on your wells, and those 5 reflections have names and have depths in the depth domain and have times in the times domain. We call it time depth pairs. You can use those time depth pairs as your flags when you use time to depth conversion. Yes. Again, I'm going to jump. I know it's maybe looks silly a little bit, but I'm going to jump this just to come up with example for seeing subsalt of the VSB and seeing below some reflection, some good things about the VSB that you can see some of the deeper reflection than what we call it prediction ahead of the bet. So if your well ends here, you still can see some of the data below it using the VSB, while what's around is your seismic. And this is a good thing about VSB. Actually, we are running here a very detailed work about check now about the VSB. The check shot, it is the same, exactly the same technique like what we are doing on the VSB, but the end result is not like what we have on the VSB. So we do have the time depth tables. We do have the relation between the depth and time through the velocity, and we can directly relate this into our data. Now the sonic, the last one in our measured velocities, all of us are aware with the sonic. And we know that the resolution is 1 to 2 feet, very nice resolution. And also the frequency content of the seismic is very high compared with the frequency content of the VSB and check shot. Here we are talking about 30 more or less gigahertz, while what we call it here is only from 10 to 125 hertz. So look at the difference. This is talking about megahertz, while the other one, the check shot and the VCB are talking about gigahertz. Yes? But we already learned what the difference between both velocities. There is what we call it full wave sonic, where we have the B and S waves. And actually, in this case, the importance here not to measure only the velocity of the B waves, but the velocity of the S wave also, in order to use it on the prediction and detection of the fluids. Because we know if we use both of them, that the B waves go through fluids, while the S waves does not go to the fluids. So the difference between them, we can calculate the most important rock properties. Either it's include gas or water, or even sometimes oil. Again, this is out of us. Now, very important stuff, we use the velocity on them, what we call it sonic calibration. Now, can we have a very nice sonic that ties at the surface of the earth, at the same time have no problem against the shale? This is what we call it a calibration of the sonic. If you do have a check shot and within the same well, and you have sonic, in this case, you are a hero, because actually you can calibrate your sonic and mix and have another calibrated sonic that added the good part from the check shot into this part that you didn't record it at the sonic. At the same time, you can calibrate the part against the shale from the check shot. So you get two things from the check shot. You get the first part that's not covered by your sonic, and also the good part against the shale that you have some problem from it. You can borrow them in a way, what we call it calibration, and they come up with a very nice calibrated sonic. And this what we call it measured calibrated sonic feed. I'm going to jump to this because actually I'm just highlighted it that in addition to the measured velocity, we have what we call it calibrated sonic rather than only sonic. We have check shot, we have VSB, and we have sonic, and add for them we have calibrated sonic. Because when we go to and do a synthetic seismogram, this synthetic seismogram does not use the sonic directly, but use what we call it calibrated sonic in order to come up with very nice synthetic seismograms that tie your well into your seismic. And in this case, you have to take care, because we are using measured velocity from the sonic, and we are using measured velocity from the check shot in order to come up with a calibrated sonic that is not equally sampling. In this case, it's not instantaneous all the time. It's instantaneous only on one part, and it is not instantaneous on the shallow part, and also it's calibrated against the shale reading. Okay. Actually, here I'm just gonna jump on how we can calibrate the velocity of the sonic, but at the same time, we come up with what very important, what we call it B wave log. It's a sonic, calibrated sonic. Some of the programs call it B wave log rather than call it calibrated sonic, but it's calibrated sonic, and we use this one in our 3D velocity model. We use the time depth table from the calibrated sonic that we used it to drive the time depth table and to drive our synthetic seismogram. Also here, the synthetic seismogram, I'm not gonna go through it, the datum and the problem of the datum. Also, I'm gonna jump all of this. And talking to you the estimated velocity. The first slide, which I mentioned, is very important, talking about measure the velocity. We covered them. We know how to get it. We know the steps, how to get those kind of velocity, which should measure the velocity, either through VSB, through check shot, or even through sonic. And then we learned what we call it calibrated sonic. Now, the other sources of velocity come up with the estimated velocity. The first one of the estimated velocity, we call it NMO stacking velocity. And this is simply where we have the source and different receivers, or if you are shooting in middle and you have different sources with different receiver, and you would like to come up with a vertical reflection, a vertical pass of the waves, and then the reflection, we have to do some sort of correction. And this correction called NMO. And how we're doing this? Using what we call it stacking velocity. And this kind of velocity, we do it through the processing itself and using this simple, very simple hyperabola type of work. As you can see, this reflection, we can correct it, and we see it on the next slide. And actually, we saw it even at the beginning, and we can correct this and make it looks like horizontal. It's not horizontal, it's just come up to each other because actually they're coming from the same point, and then we stack them. And this kind of velocity, we can use it. And we can derive another velocity from the NMO velocity, call it what? Root mean square velocity. It's driven from this velocity, and it doesn't, as I mentioned, doesn't have any rock property. It is just a number. Using the Beck's equation, it's just a number in order to use it later on. We will see how we can use it. Yes, in the front of you, now I am putting you the hyperabola from one shot. Actually, this is a CDB, and on the CDB, there is different hyperabola change. And this hyperabola change have been migrated using, or have been treated using this kind of velocity, the NMO velocity. This is an interesting shape, where to the left-hand side, one with NMO correction before doing the velocity analysis, and to the right, the one with to the right-hand side, where this kind of hyperabola has been collapsed, and it's ready to be stacked after that. So this is one CDB. I'm going to jump on this. There is a way, different way in order to pick up the right velocity, but I'm going to give you this only, how we are picking our velocity. And we are picking what velocity, what we call it semblance, where at each level of that level, so the left hand, this is one CDB, and this is what you call it, what you see at the color. Here is your interval velocity, interval stacking velocity, just to be precise. And actually, we are using the machine in order to stack, say, this very nice bright reflector, and we're going to change this velocity and see how it's changed by changing the display. 1, 2, 1, 2, 1, 2, I think you can more or less follow exactly how the change of this is happening right at that location over 900 millisecond. You can look at that here, there, here, there, here, there. Very, very interesting. So it depends on the guys who are doing the picking itself. So if the processor picked something in the middle, it's gonna stack something here. If he picked it a little bit at the left hand side, as you can see here, right, left, right, very different, very different. Watch the reflector at the 900. While I'm moving it forward, backward, forward, backward, forward, backward. So it does change the position of the reflector itself. And this depends on what? Depend on the interpreter himself or the guy who are doing processing. If he picked it right, or he picked it wrong. So that's why if the estimated velocity during the processing, it's a kind of erroneous type of velocity. It's not as good as the measured one. I just try to make sense to like the sense of what we are doing. There is different way of doing this estimated velocity. So the NMO velocity actually in the middle is the corrected one, and to the right is the uncorrected one. To the left is overcorrected one. So the one in the middle is the corrected. So after that, we stack them and come up with very nice trees. So it's statistically it do a lot of work, but by the end of the day, it depends on the interpreter of this data. The processor himself, he is the owner of this data, and he consider himself the interpreter of this velocity. Yes. By the end of the day, you can display something interesting in the front of you, each common midpoint, at the same time, the time, and then the velocity at each time. So you can come up with these nice velocities and take care that we are putting time 0 while velocity 1500. This is the velocity of the water. So at time 0, it's a velocity 1500 because we consider our reference the water, and the water velocity, in this case, marine data, it's 1500. But you can display this nice velocity vertically. And this is a kind of interval velocity. Now, I would like to mention something for you, that what we are measuring, and we consider it as measured velocity, is an interval velocity representing the rock. So when you measure the velocity inside the well, in the front of your layer, you are measuring the interval velocity inside the rock. And this is considered as a property of the rock. While the average velocity that you measured it from the top to the bottom of the layers, from top of them to the bottom, is not a property of the layer. While it considers only the distance, and that's why we call it average velocity. Then if I asked you the average velocity or the interval velocity, which of them are property of the rock, directly you will answer it is the interval velocity, not the average velocity. Yes? DMO velocity, we'll consider it on the previous slide that we mentioned, because actually we are calculating our NMO using the assumption of flat horizon, while my horizon is dipping. In this case, my velocity have to consider also this dipping, and that's why we are adjusting my NMO velocity to be DMO velocity, considering the dipping itself. And this is add or subtract some of the velocities that I earlier do. I'm in the front of you putting different shapes of how this DMO could work. So actually, on the flat surface, you have very nice point, and then you can collect your data directly around it. Once it's depth, so it could be like this one, could be like that one, could be there like that one. So it's different. So we have to take in consideration all these kind of shapes in case of using the DMO. Actually, on the processing, they call it common receive and gather, common offset gather. All of this were taken them in consideration in order to adjust our velocity. RM velocity, as I mentioned, it's just a velocity we did it using an equation, but it doesn't reflect, as I mentioned, any rock properties. We are using, I'm also calculating using this, but actually this velocity is important for us in order sometimes on the depth conversion, we will learn how we can use it in this case. Because what we get from Dick's equation is usually RMS figures for the velocity itself. So as I mentioned in number 5, RMS does not reflect the rock property. Okay. Migration velocity, as I mentioned, it looks like exactly like the NMO velocity and the way of the estimation itself. So actually, in this case, we are doing interesting things that the dashed line represents what we are recording, while the solid line representing the true surface. So what we call it, we push the reflector up depth. So the reflector was here, we push it up depth using the migration velocity. So the velocity that will correct this dipping will be in this way and will be used sometime. Now, the processing center usually give you as an interpreter, if you are talking about 2D, if you're talking about 3D volume, he give you a volume of velocity, he call it stacking velocity, and he can give it you like sig y, or he can give it you like 0.5. Or he can give you a migration velocity, which again, at a value more or less, it's very near to the NMO velocity, but it taken on consideration the adjustment plus or 10% for the NMO, for the dip move out, and for the migration. So usually we use the migration better than the stacking velocity. Conclusion for you for now, that we went through measure the velocities, VSB, check shot, sonic, and we added another one called calibrated sonic, yes, or B wave log. And then we move to, and we know that all of those are measured the velocity, they measure the interval velocity inside the well, and they are our first category. Our second category actually would be calculated, we didn't mention yet, but we will mention. And then our third category is the estimated velocity. And the estimated velocity, we went through the NMO velocity, and then we went through the DMO velocity, and then through the migration velocity. All of them are estimated velocity. I'm here concluding that the key difference between stacking velocity estimation and migration estimation is that the stacking velocity only require individual CDBM gather. This is an important notice. That all what you need is the same B gather. While in the migration velocity, you require pre-stack data set in entry. All the data set. So look at that. The migration velocity, in this case, you are using all the data set in order to calculate the velocity. That's why it's more or less the stacking velocity is much recommended if you have stacking velocity and migration velocity. The migration velocity is more recommended than the stacking velocity, because the stacking velocity is dependent on only CMBs or Ben, while the migration velocity, it takes all the data as an entry. Yeah, it's worth mentioning out. What we call it pre-stack time migration velocity, something I'm not sure if you are aware with or not, but this is a typical business trademark, which is the pre-stack time migration, pre-stack depth migration velocities. Those kind of velocity needs more or less the input from the interpreter. So we use the time data, the time migration data, the normal pre-stack time migration data, and that's why when we say pre-stack, it gets all the data together in order to come up a figure about the migration velocity. And then we stack it before doing anything. Actually, you can, what we call it pre-stack depth migration data, you will see it on the next slides. The pre-stack, the NMO and DMO and pre-stack migration data, all of this, we are not incorporating the well data. So there is no well data have been driven, and there is no adjustment up to now. Actually, on the processing, we used to give the processing center some of the wells. just to give them a clue about the change of the velocities among the wells themselves. But doing all of this comes without any introduction to the wells. Once we started to put our wells, we put our wells with our time depth tables that include time depth pairs. It will tell you at each time what's the depths. In this case, you know your velocity from the wells, and then you can go into what we call it pre-stack depth migration. Before talking about pre-stack depth migration, I would like to highlight some of the topics because a lot of the colleagues have some confusion about some definition. Average velocity, so it's a simple average velocity from top to the from the surface to the top of the target. Very simple. Have 10 layers, so it's an average of the 10 layers. Have 8 layer, average of the 8 layer. Have 2 layer, average of the 8 layer. Simply like this. Yes? Interval velocity, it's measured the layer itself. So it measures the top of the layer, the base of the layer. It measures the velocity in that case. Yes? Now, if I have a limestone, and this limestone is 100 meter thickness, and when I measure my velocity using my VSB, I got 4 or 5 readings inside this 100 meter. You will find a difference between those 4 readings within the same layer. And this is the good things, that you are sampling the interval into 4 intervals in this case. While if you got the top bottom, it's an average in this case, while you can consider it interval. So now think about that. It's 100 feet, while you have sampled every 25, and every 25 you get a figure of velocity. In this case, the figure are 4 velocities, could be very near to each other, or it could be only one value. If it is more or less homogeneous limestone with one velocity, interval velocity. Think about that, because this is very important. When you're talking about interval velocity, you have to look into your sampling within your interval in order to understand what's the definition of interval velocity and average velocity. You can have within this interval 4 intervals, so accordingly you have an average velocity in this case. Yes? Think about that. So the average velocity is simply VA, Z over T. You can get it. Root mean square velocity, as I mentioned before, it's very simple. Have some summation of the V's T at the time 0. And this is what we call it VRMS. And again, this formula works with 1 or 2 at a time. So the RMS either in 1 at a time or 2 at a time, you can use it. As I mentioned, it doesn't reflect the interval, the property itself. Yeah, I'm going to jump this. Pseudo velocity, and this is our main problem issue in our business. This is your seismic, this is your depth, and I'd like to calculate the velocity. This is my target. So I measure the time from the 0 level into my target, 2 time, and divide by 2, get the 1 time. And then I have the well. I get the depth to that target. So I simply divide the depth into my time and come up with a velocity. And I call it average velocity. No, it's not average, it's a pseudo, because actually I calculated the time according to measure the center of the beat in here. Well, actually, when I'm measuring the center of the beat, I wasn't a little bit focusing. I measured more or less the white, little bit white track or the zero crossing. In this case, my measuring for the velocity is going to change, and that's why we call it pseudo velocity. Yes, so make sure when you are depth converting your data, if you are using the real velocity measured inside the well, or you are using the pseudo average velocity, because actually we have to usually in the business We do a maps using the pseudo average, and we do a map using the real average velocity, and we compare between them to check out the velocity model. Now, those are the four: instantaneous velocity, average velocity, interval velocity, root mean square velocity, and then a pseudo average velocity. Those are the different type of velocities. Now, simply, when we do depth conversion, we do what? We've got the time velocity, and we come up with depth. If you just use this, so in this case, you are using a more or less a calculated velocity, because you didn't mention what kind of velocity model in here. Is your model include a measured velocity, or your model include only migration velocity, as example, estimated velocity? You have to think about that very carefully. Actually, the depth conversion method, choosing appropriate method. We have to, in order to change data from time to depth, we have to think in different things. What kind of data you have? You have check shot, you have VSB, you have seismic velocities, you have migration velocity, what? So before you do depth conversion, ask yourself this question: what kind of source of data I have? Do I have any kind of measured velocity, and list them? Sometimes you have 10 wells in your area. 2 of them are 2 VSBs, the other have check shots, and the others have only sonic. You have to list and check carefully each one of them. I looked at many different models, and I discovered by the end of the model that the guy didn't use all the data in their hand. So start with what kind of data you have, and decide according to slide number 1 with the measured, and then add any kind of velocity after that. And you're going to go with the measured and come back to the measured at the same time. Also, look at your geological complexity. Are you dealing with very complex geology, like very big area of salt dome, like very complicated inverted area, like whatever? Or you have a very simple, very nice geology. So if simple, go a simple way. If it's complex, try to think about which way to start with. If you find that the simple is still working, use the simple. We never go with complex velocity model without needing them. But we usually do many different models and look at the one that fits the real data by the end of the day. Yes? Now, the third question, ask yourself why you are doing depth conversion. Why you are doing depth conversion? Are you doing depth conversion in order to, for a prospect, as example, to calculate volumetric, or to prepare well plan, or to convert our volume in from time to depth? We have to do that. Actually, according to the previous 3 topics, we can either do very simple single layer method of velocity, or multi-layer of velocity, or what we call a 3D grid velocity. Each one of those models, you can run it on the same basin, on the same data. You can run it with a single layer for your target. You can run it with multi-layer. You can do what we call it layer cake, or you can do a 3D grid velocity model. Now, the art of the business is talking about using the 3D velocity model, where most of the data that we mentioned are available. In order to do a velocity model, you have to go through more or less 3 or 4 steps. First of all, you have to analyze the geological sequences that you are talking about. You have to divide them into different intervals according to what? According to the well data. So, as example, you go through a cross section through the wells, and you come up with the sonic displayed at each well, and look at the interval where your velocities are variable, where are they are changeable. and pick up those intervals. And usually we call those intervals as flags for the velocity, where at that interval, the velocity dramatically change, or they are increasingly, you can see them increasing. Taken in consideration the assumption of that the velocity increase with depth. Now, look at the panel in the front of you under velocity. So I have a clay stone from the sea level to the top chalk. I have a clay stone, and then I have chalk, and then marl, and then mixed clay and sandstone. Each one of those intervals got its own velocity and its own thickness. Of course, an example, the clay stones from the sea level up to the first layer from 1400 to 3000 feet thick. So I know that this interval is changeable for almost the double sometimes. Accordingly, its velocity are changeable from 7500 into 6000. So this is the range of change of velocity. You have to understand this before you do any steps, before you do any step of depth conversion. You have to understand the geology and the variation of the thickness of your interval that accordingly change your velocity. And then you go to the second interval, and then the third interval, do the same for all the other intervals until the end of your model. Actually, you can see that where I highlighted this as velocity inversion. So this is 5800 to 14500 feet per second. This is velocity. Actually, it decreases when you go from the top shock to the base shock and then the base Cretaceous. In this interval, it drops. You have to take this in consideration, because if you are using any kind of models, theoretical models, this is going to change, going to do a problem for you, because the assumption of the seismic does not put in consideration this velocity inversion. That's why I'm telling you, before doing anything, study the data that you have. First of all, look at the data is available in your hand. The second, after that, you put priority. Is it measured? Is it calculated? Is it what kind of source? And put some question mark about the sources that you don't trust them. And then from that, ask yourself, should I go simple model? Should I go with complex model? Or should what do you do? And before choose the best model, study the geology very carefully, and the interval thicknesses change and the interval velocities change on your area. And it's very good for you to look them laterally all over the area that you're going to use this model on. This is your first step. Now, you have to tell yourself which the project that you are going to use it. Are you going to use it for frontier exploration? Are you going to use it for the appraisal well? Are you going to use it for field development? Or what? Accordingly, there is some recommendation with some kind of velocity data that you have to be available in order to do so. So if you are using it for only just one velocity in an exploration area, then it's easy. One simple well, one simple value, and that's it. Yes. While if you are going to field development, no, in this case, you have to take care about thinking about more deeper on this. The second step, the first step, we mentioned it about how to study carefully your intervals and your subsurface thicknesses and velocity, and then the next, what's velocity function to use? Should I go with the simple average velocity? Should I go with pseudo velocity? Should I go with layer cake velocity, or what? Now, in order to choose what we have, those are the 5 or 6 ways of time to depth conversion on the market. So what we call it V naught K function, it's a very simple linear regression one. And then polynomial functions, another one. And then what we call it Faust function, midpoint depth function, velocity versus time function, and then isochron or isochore function. Each one of those, actually, we cannot finish them on a lecture, but each one got advantages and disadvantages. But start with the simple, and then after that, add whatever you would like to add. Yes. Here, actually, I'm more or less in details on the V node function, which is very simple. We draw the relation between velocity and depth, and come up with as a linear line. And then actually from that linear line, we can calculate from the slope, the velocity itself. So where the intersection here will give you the V node. And from the slope, you can calculate the velocity. And this is a simple way where you have a lot of wells, and a lot of us are using it. But usually this method have a problem on good tie at one well and one well or two wells, and have another not good tie at other wells, because again, it's a kind of modeling. Okay, I'm not going to go more with this, but I'd like to jump directly to a polynomial, which again is not representing the relation between on the depths as a very nice straight line at the previous one, but it does take in consideration the polynomial shape of our time depth relation, which much better, of course, than the previous one. But again, I can try this one and I can the previous one and come up with a velocity model using the linear regression, and come up with a velocity model using the polynomial function, and come up with depth map and look at the difference between them. Each one could reflect something different, and it's a velocity modeling. It's not only one solution, it's different solution, and you have to decide which solution is better for your data and for your target. As I mentioned, it depends at which part. Are you in development stage, are you in prospect stage, or whatever. Yes. Again, I'm not gonna talk too much about this, but I'm gonna end with two things, which 2D grid velocity model and 3D grid velocity model. For the 2D grid velocity model, it's very simple, where I'm supposing that you have a time map, and you have 5 wells or 4 wells. And at those 4 wells, actually, you have the depths of the layer. And either you have a velocity also for that layer, the average velocity from top to bottom. Then if you do have an average velocity measured at the well, then you contour the values of average velocity all over the area. Of course, it's going to be very corrected at the well location, and as you go away from the well location, more it deteriorate. Yes, but again, this is c'est la vie. We cannot do more than this. Yes. Okay, so I'm going to end with a grid for the velocity, for the measured velocity at the well. At the same time, I have a grid for the time. So I can multiply the one-way time, in this case, grid, with the velocity grid and come up with depth map. This is what we call a 2D grid velocity model. Very simple. You can do it either using the measured velocity from the well, or the pseudo velocity, time from the seismic, depth from the well, and also do a 2D velocity model using the pseudo velocity. And you come up with a model and look at that model. The difference between that model and the previous one that used the measured velocity. All of this, we call it a 3D grid velocity model. At the computer, all of these options are very simple, very simple. It took only 2 minutes or 3 minutes to do it. Once you have your time grid available, your reading of the velocity at the wells available, you can in 2 minutes come up with a very nice velocity model. And you can check it on the fly directly if you are using any kind of software. Now, if you want to do a 3D velocity model, now the story is different. Why? Because easily you have to put a certain type of input in order to do a 3D velocity model. What is the difference between the 2D velocity model and 3D velocity model? For the 2D velocity model, each point on your map, each X and Y, have one reading, which is the reading of the velocity. When you have a velocity map, each X and Y representing well, or even representing a shot point, got one reading for the velocity. There is no velocity variation on the vertical direction. While on the 3D velocity, there is time variation at each location of x and y. Accordingly, there is a velocity variation. So time 0, velocity. Time 1 millisecond or time 100 millisecond, velocity. 200 millisecond velocity at each. So they got another dimension. So you have to take in consideration and thinking in a 3D in case of 3D velocity model and in 2D in case of 2D velocity model. In order to do a 3D velocity model, I'm not going to show you the steps on the that we do it on, but at least I'm going to show you the concept. What's your input in order to do that? Your input would be the well tops that we consider it the Bible of the depth conversion. These tops represent the depths of the target that I'm going to use it at the wells. Actually, in the wells, I have 5 or 6 or 7 layers. So I have to get the well tops of the 7 layers at each well, including on my calculation of the velocity model. Yes, now. So I have, say 5 or 6 or 7 tops. I have at each well 5 or 6 or 7 tops. Those well tops have been defined by the geologist and taken consideration that the geologists sometimes put at the wells not the real top but the faulted tops. You don't need those faulted tops. You need the well tops themselves. If the fault is faulted, if the tops is faulted, don't consider it. It will cause you anomaly on the velocity. Then consider only the top that the geologists consider it at the real top of that interval. Yes, those intervals, we start with them at the same time, we'll end with them. We'll calibrate everything to make sure that my horizon will tie them correctly. The second things, which is the seismic surfaces covering the dynamic range of the volume. If I have a 3D volume, and this 3D volume, I have 7 layers. Those 7 layers, I have been mapping them through my seismic. I'm going to use those layers. And actually, they're going to give me the behavior of my layer in between the wells. If I have 2 wells, I don't know exactly if my reflector is going up between the 2 wells or going down between the 2 wells. Who will tell me, who will describe to me the behavior? My surfaces. So I'm going to use my surfaces as a guide for the change of the position of my reflector on the seismic. Then number 3, the time depth table. The time depth table. The time depth tables come from what? Come from our measured velocities, which could include the check shot, the VSB, the calibrated sonic, or whatever. Yes? This is gonna match time depth tables for me. The last things, which are the stacking or migration. So what I'm gonna do on the idea of having those 4 manager, I'm gonna use the stacking or migration velocity volume. I'm gonna calibrate it with the time depth table at the well location. I'm gonna distribute the difference in between using my services, and then I'm gonna come up with a 3D velocity model. And this 3D velocity model got very accurate shape. Actually, here I'm jumping to the uncertainties. I don't need it to. This, I just wanted to show you this. This is what we talked about. If you have top and bottom, and you divide your interval directly into interesting interval, and you know exactly the variation of the thickness of your interval and the variation of this interval with velocity. This is very important. And then I just got out of this with full screen just to show you a shape. Come back to full. In the front of you, actually, this is a typical This atypical 3D velocity model, and the inline, cross line, and time slice are showing the volume itself after distributing the calibration. And actually, this 3D velocity model, we use it directly to change from time to depth. To conclude my talk today, we went through very simple definition of the velocities, and then the measured and calculated and estimated velocities, and we differentiate between some terms about the velocity, and we know now which one to choose and to use. And also at the same time, we talked about two different models to change from time to depth. One of them is the 2D model, very simple one. The other one is the 3D velocity model, which usually the market now in the market we are using this kind of velocity, but it depends on the data on your hand, depend on the target that you would like to do, either for prospecting or for development of a field, or just for leads or whatever itself. I think I'm done for today, and maybe if you are interested, we can continue on a second time concerning how to do this workflow itself. Exactly, step by step, how to do it. If you are interested, I just flied over the philosophy of the depth conversion and some of the very principles that you need to learn before you start to do any kind of depth conversion. Now, I'm very open for any kind of question. Either I can see the Q&A.
Thank you so much, Dr. Ali, for this informative session and for your time and effort as well. I'm sure we all benefit quite from it. So now for a quick Q&A session. For the first question, we have someone is asking, what is the meaning of CDP?
Yeah, that's a simple question. Let me come back to one of the slides to answer it directly.
Okay.
It's again principles, but it's a good question. I think you still can see my screen, right?
Yes.
In the front of you, we are assuming that we are shooting in that position and have reflection vertically. But on the real life, we are shooting from side and recording from other side. So the same point in this case have been recorded first time from S1 to R1. And for the second time from S2 to R2. For the third time from S3 to R3. So I have been recording a reflection from that point 3 times. So the waves have gone through it 1 time, and then it become common for the waves because it went through it 2nd time and then 3rd time. And so that we call it common depth point. So it's a very common depth point for the waves. It went through it 3 times. It visited this position 3 times. And we are using these techniques to average the noise and cancel the noise from the signal itself. Because after that, we are going to stack them as only one ray pass. Those 3 passes would be averaged together and come up as shoot from this and come back on the symbol. And this common depth point, it's a very common technique, very old technique on the data acquisition on the 2D, and it got a parallel one on the 3D where we have the bends rather than points. It's an area we have the reflection from that area. It's called the binning. So the CDP and binning, it's a way of shooting of the data in order to cancel noise and increase the signal to noise ratio.
Thank you. And we have another question. Someone is asking, how can seismic velocity be used to determine the thickness of a layer?
Well, very simply, the answer is very simple. You have the thickness of the layer. Say you have one well. I'm going to assume this. You have one well, and this well have penetrated my layer. So I know exactly the thickness. But I'd like to test how can the velocity will help me. Yes? So I have the time to the top and the time to the bottom. Let me use this also. So I have in the front of you, this is top my layer, and this is base my layer. So I know the thickness of the layer from the well. Say it's 100 meter. Yes, but I'd like to test how can I calculate the thickness of my layer. I know it's 100, but I'd like to test it. So I have the time from here to here, which is two-way time. So I measure it by 2. I divide it by 2 to get the one-way time. And then I multiply this two-way time with the velocity that I measured at that well. I can come up with thickness. I'm going to compare the thickness that I got it from here from the thickness of the well to make sure that it's the same thickness. Very simple.
And another question is how RMS and average velocity are different?
How again?
RMS.
Usually, yes, the RMS usually it's different than the average. Usually it's higher. With a percentage could reach 15%. And that's why we are not considering as a representative for the property for the rock itself. We use the value on the calculation because you have to use it for the migration, you have to use it for some of the equations. But it's not representing the fluids as example. It's not representing the porosity as example. So it's not indication about the property, the rock property. The interval velocity can, while the root mean square, it's a root mean square. It's more or less a figure come from the equation, not directly from the lithology itself. Yes?
Okay, and the last question we have, if we apply the Dex formula on the stacking velocity, does that make it an accuracy as calculated velocity, even if it's based on estimated velocity?
That's a good question. Look for input and you look for output. So if I use my input is measure the velocity and I use the calculated, in this case, my calculation will be very good because my input was measured and the calculation is just an equation. If I put estimated velocity and they come up with calculated velocity, then I know I am putting estimation. So look your input and expect your output. Don't expect to put estimated and then receive something good. No, you still receive something built on an estimated velocity. That's why I put the concept of the velocity on your mind. At any time, you will be able to choose which one I should use. Okay?
Okay, thank you. Thank you so much, Dr. Ali, again. And thank you all for your attendance today. Highlighting that this session is recorded and will be uploaded soon on PioPetro YouTube channel. So make sure to subscribe on our channel. Thank you all and bye.